All right. This video is going to be fairly quick here. It's called the Nernst equation. It is in your notes, like page 5 of your notes. Basically, cell potential at non-standard conditions, like that little E cell. When you see like standard conditions, that means like the concentrations of things are 1 molar. If there's a gas involved, to be 1 atmosphere pressure. So standard conditions is when you see that little thing right there. So we're saying they're changing some things like that. We don't really do a lot with this, but we're going to worry about more like Le Chatelier's principle, where if we change something in the cell, in this battery, if we change something like the concentration of copper ions or the amount of zinc, solid zinc that's in there, now what happens to the potential of this cell is what we're going to look at. So I'll kind of go through this stuff. We're going to really worry about one part of this. This is they're showing this is an equilibrium here. Again, if you want to find your cell potential, got to figure out what's being oxidized, what's being reduced. Well, zinc is going from a 0 charge to a +2, going up in charge. So that is being oxidized. Zinc's being oxidized, so you look up the oxidation potential of that. Okay, it'd be the reduction potential on your sheet, flipped around. And copper's being reduced, so look up the reduction potential of that. Add those two together, and there's your cell voltage. Your voltage here is 1.10 volts in the forward direction. So it is a spontaneous cell in the forward direction. Negative 1.10 volts. I guess if you're going the other direction, you have to make that happen in order for that equilibrium to happen the other direction. If we think of this as an equilibrium, if you think about what the K expression, or Q, remember when you're not necessarily at equilibrium, but the K expression for this would really be, since this is a solid and this is a solid, our Q or our K, okay, remember Q is really just K, maybe not at equilibrium, would really just be the concentration of zinc over the concentration of copper. Remember, concentration means molarity. And at standard conditions, those would be 1 molar solutions. At standard conditions, those would be 1 molar solutions. All right, so we're going to think of this as Le Chatelier's principle. Okay, Le Chatelier's were like, if you remove one thing, the equilibrium shifts to replace it. If we add something in, the equilibrium shifts to use it up. So we're going to think about it as Le Chatelier's principle in equilibrium stuff. So what happens if the concentration, molarity, of copper ions is increased? So if we would increase this concentration, the best way to do that would be add like solid copper nitrate that dissolves. You get more copper ions in solution. If we increase this concentration, the equilibrium is going to shift to the right to try to use up those copper ions. Okay, you're going to shift to the right, try and use up those copper ions, which means that if we shift to the right, your cell potential will increase. Okay, there's a higher voltage. If we can get the equilibrium to shift to the right, your cell potential will increase. So if we increase this molarity of copper ions on there, it's going to shift right. Your voltage will increase. Okay, if we increase the zinc concentration over here, it's going to shift back left. Okay, you're going to shift left, and your cell potential will decrease in that case. All right, I'm going to skip the Nernst equation. We do not have to use the Nernst equation for anything. It is a big, long equation. It looks something like this right here. It's probably on the blue sheet. All right, we'll talk a little bit about it at some point in time, but we do not have to use that right at this point in time. So we're going to go down, and this is what I want you to be able to do. This is kind of conceptual stuff, not mathematical. So given this reaction, so if we think about this as a cell, anode and a cathode, I'm going to make this my anode. Remember, oxidation occurs there, red cat. Really what we'd have here is we have zinc going from a 0 charge to a +2, so that's being oxidized. So we have really be a solid piece of zinc turning into zinc ions. And we have, on the other side, we have a solid piece of iron. That is over here, and you have Fe+3s turning into Fe's as this reaction goes. Okay. There's your oxidation, there's your reduction. So I actually want to know a couple things here on this. I want to know what happens to the cell potential, the voltage of the cell, if we make these changes. And I want to know what happens to how long the cell would last. How long would your battery last? So that's just like a limiting reactant type of thing. Like, how long would it last? So remember, standard means these are 1 molar to start with. So at standard, your cell potential is when those are 1 molar. So if we change those molarities, that will change the potential of the cell. Change those molarities will change the potential of the cell. All right. So let's say that the size of the zinc electrode is increased. Size of the zinc electrode is increased. So we make this a bigger zinc electrode. In other words, we're increasing the amount of zinc. Well, if we think about equilibrium, solids don't affect equilibrium. Our K expression was this concentration over this concentration. Solids are not involved in that. So increasing the size of the zinc electrode does not do anything because it is a solid. So no change in our cell potential. It'd still be the same voltage, but we now would have more zinc. Think about it. The zinc is turning into zinc plus 2, so this electrode's getting smaller as zinc is becoming dissolved. If we have more zinc, our battery would last longer, assuming we have enough iron ions to react it with. It would be a longer lasting one because we have more reactant available, assuming we have enough iron with it. Number 2 here, 50 milliliters of 1 molar iron nitrate is added. So that means we're adding some 1 molar iron 3 nitrate. In other words, we're adding some 1 molar iron 3 ions. Well, normal means this concentration was that. So the normal cell potential or standard cell potential would be when it's 1 molar. Adding more of it doesn't increase the concentration of it. It's still the same concentration. So this concentration would not be changing. So since concentration is not changing, the cell potential doesn't change. But we did just add more iron ions. So adding more iron ions will make the cell last longer. So same thing as that one. Same thing as the first one. No change in the potential of the cell because it's the same concentration of iron ions, but the cell will last longer because we now have more reactants, more iron ions, assuming there's enough zinc to react. Third one, solid zinc nitrate is added to the anode. So they're adding zinc ions in the anode. They're adding zinc ions in there. Well, if we think about it this way, if we think about it, Le Chatelier's principle, if we add solid zinc nitrate, that means the zinc nitrate will dissolve, which means we're going to increase the concentration of zinc ions in there because we're adding solid, so it's going to dissolve, make more zinc ions. So we're increasing this molarity. Well, the equilibrium wants to shift to use that up, so our equilibrium will shift back left. Okay. Add zinc, shift back left, which would cause the potential of the cell to decrease. So a decrease in the cell potential at that point in time. Since that is a product in the reaction of equilibrium, it would not change how long the battery lasts. So since zinc is being produced as this reaction goes, it would not change how long it lasts. You just have more of it at the end. All right. Fourth one, the size of the iron electrode is increased. So we're making this iron electrode bigger. Now, if we think about this iron electrode, all it's doing is it's getting bigger anyways. As this reaction goes, these iron ions are turning into solid iron. It's getting bigger as it goes. Iron's not part of the equilibrium. If we increase a solid, it doesn't affect the equilibrium, doesn't make it shift either way. So there'd be no cell potential change there and no change in the length of the battery. So no change at that point in time. Fifth one, the concentration of iron nitrate is 3 molar, and this is 0.5 molar. So normally they're at standard conditions, they're both 1 molar. So we're increasing the iron concentration, increasing that concentration, decreasing this concentration. Well, increasing the iron concentration means the equilibrium wants to shift to the right, try and use up those iron ions. Decreasing the zinc concentration, equilibrium wants to shift right, try and replace those iron ions. So your cell potential here would definitely increase. In terms of how long the battery would last, we now have more of one of the reactants. So it would be a longer lasting battery. So it would last a little bit longer in that case. Last one here, some solid NaOH added to the cathode. So they're putting NaOH in there. So that's going to make sodium ions and hydroxide ions. So if the hydroxide ions react with something, then we're going to end up with a change there. Well, if you think about it, our Fe+3s that are floating around in there will react with hydroxide ions and make FeOH3, which is insoluble. So the hydroxide ions from the sodium hydroxide will react with that. So we're going to remove iron ions. So we're going to take iron ions out. As these get removed, equilibrium shifts back left, cell potential goes down. Okay, so that would cause the E of the cell to decrease. And since we're removing one of the reactants, shorter lasting